In this video, I will show you how to glance at a polynomial function and know the end behavior, as well as to know the possible number of zeros or x-intercepts and the number of turning points, meaning if I have a graph that goes like this, here's one turning point, that would be two turning points. So you'll know that. And I'll show you how to find the actual zeros of a few basic functions. But first, let's talk about end behavior. If I go to desmos.com on my computer, I can easily look at a few graphs and kind of play around with it. Let's start with one that we know. If I do x squared, right, we know that that's a parabola that looks like this. Now look at the end behavior. Now notice how it rises on the left and it rises on the right. Would it surprise you to know that if I replace this with the fourth power, it didn't change very much. The end behavior stayed the same. What if I made this the sixth power or the eighth power? Hopefully you're seeing that any even power is going to have the same end behavior, just like x squared. It rises on the left, rises on the right. Now let's go back to x squared. If I make the leading coefficient negative, okay, lost my little cursor for a second there. If I put a negative in the front, see how it just turns the whole graph upside down, okay? And then again, it doesn't matter if this was the fourth power or the 20th power, the end behavior remains the same, okay? Now, what about odd powers? If I have x to the third power, this is what your basic odd degree function is going to look like. Okay? Now, it turns out that this is going to be the same no matter what the odd power is. And I'm just talking about the end behavior. If I made this the fifth power, notice that the end behavior stays the same. Or the seventh power, the end behavior remains the same. Okay? Notice if you look at the right-hand side, right now this is positive and the right arm is in the sky. If I make this a negative leading coefficient, now because it's a reflection over the x-axis, everything turns upside down, but focus on the right-hand side, now the right arm is facing down. So this is going to lead us to something called the leading term test, because that's what's going to matter. Okay? Say if I have 2x to the third power minus 4x squared, okay, plus 2x minus 5. Okay, so I've got this. Now, look at the end behavior. All that really mattered was the first term. Okay, the fact that this is x squared and plus 2x and minus 5, that did not change the end behavior. This has the same end behavior as x to the third power does. All right, all that really matters is the first term for the end behavior. Okay, so with that in mind, we can use something called the leading term test to know what the end behavior is going to be like. So, looking at the leading term of this problem, because the degree is odd and the leading coefficient is negative, okay, I know that the end behavior is going to be like this. Okay, remember that for the odd ones, where you have one side is up and one side is down, focus on the right-hand side. If it's negative, then the right-hand side will be down. Okay, so then of course we could go ahead and write the actual end behavior. We're supposed to describe the end behavior of the graph, and that would be as x approaches negative infinity, f of x approaches, well, on the left it rises, so that's positive infinity. as x approaches positive infinity, okay, meaning on the right-hand side, f of x approaches negative infinity because it's falling. Okay, so on this one, the leading term is right here, and that is going to be even degree and positive leading coefficient. All right, so that means the end behavior is going to look like this. So that means that as x approaches negative infinity, f of x approaches positive infinity, and as x approaches positive infinity, f of x approaches positive infinity. Okay, now looking at number 3. Be careful. The leading term is not always first, okay, if it's not written in standard form. Look for the highest exponent. So this is actually the leading term, so don't get fooled by that. So this is even degree, and it is negative leading coefficient. So that means the end behavior is going to look like this. Okay, so that means as x approaches negative infinity, f of x approaches negative infinity, and as x approaches positive infinity, f of x again approaches negative infinity. All right, problem number 4 looks a little bit strange, but if you want to figure out what the leading coefficient is doing, all you really have to do is ignore the +1 and the -3. So the leading coefficient is going to really be x to the third power. The leading term is really just going to be x to the third power. All right, so that means that it is odd degree and positive. All right, it's odd degree, so it's going to be one arm up and one arm down. Because it's positive, the right arm should be up. So this is our little end behavior picture. So as x approaches negative infinity, f of x approaches negative infinity. As x approaches positive infinity, f of x approaches positive infinity. Okay, same with this one. Because if I want to figure out what the leading term is going to be, just take out the +4 and take out the +1. So that's going to give me negative 2x to the 4th power. Okay, so based on that, I see that I have even degree and negative leading coefficient. Okay, even degree negative. So that picture looks like this. Okay, so my end behavior will be as x approaches negative infinity, f of x approaches negative infinity. As x approaches positive infinity, f of x again approaches negative infinity. On the left it falls, and on the right it falls. And one more time for problem number 6. If I want to know what the leading term looks like, I will disregard the +1 and the -4. So that's going to give me x to the 6th power, which is even degree and positive leading coefficient. So that's going to give me end behavior that looks like this. So as x approaches negative infinity, f of x approaches positive infinity, and as x approaches positive infinity, f of x approaches positive infinity. On the left it rises, and on the right it rises. Okay, it turns out that the highest degree tells us the maximum possible zeros. And so in this case, because the degree is 5, then the maximum possible zeros, there might be up to 5 zeros. Now, there don't have to be 5. There could be 4 or 3 or 2 or 1 or none. But there's a possible 5. Now, when it comes to turning points, and again, if I have a graph like this, for example, then this is 1, 2, 3 turning points. The number of possible turning points is 1 less than the degree. So the degree is 5, so the possible zeros, 5. Possible turning points, 4. Okay, let's do that part for number 8 real quick. Possible zeros, 6. Possible turning points, 5. Okay, looking at 9 and 10. Okay, see the degree. Possible zeros, 6. Possible turning points, 5. Looking at number 10. Okay, x to the 8th power. Possible zeros, 8. Possible turning points, 7. All right, now let's go back and find the actual zeros. Okay, so the actual zeros, we have to factor this. In fact, let me zoom in a little bit. Finding the zeros, we set the function equal to 0 and we solve it. That's how we find the actual zeros. Let's start by taking out the greatest common factor, which here is x to the 3rd power. So I will take x to the 3rd power, put that out front. That's going to leave me with x squared plus 3x plus 2 on the inside. So I have x to the 3rd power, and then now I can factor this down as a binomial times a binomial. X squared is going to be x times x. 2 can only be factored as 2 times 1. Okay, and I need the inner and the outer together have to give me the middle. So like inner, I have 2x. Outer, I have 1x. I'm trying to get 3x. So I'm just going to let them remain positive. Okay, positive 2 times positive 1 is 2. So this is the correct factorization. Now, if I set each of these equal to 0, that's where I get the zeros. So x to the 3rd power is equal to 0, x plus 2 is equal to 0, and x plus 1 is equal to 0. So this is going to give me x is equal to 0, and x is equal to negative 2, and x is equal to negative 1. So these are the zeros, the actual zeros. 0, negative 2, and negative 1. Okay, so we had 5 possible zeros, but only 3 actual zeros. And really the reason why we only had 3 is because we would say that this 0 was really a triple 0. It's multiplicity 3 because it came from x to the 3rd power. All right, so this is multiplicity 3. So it sort of counts like it's as though it's 3 zeros. Anyway, moving on. Looking at problem number 8. Okay, there is a common factor here, so let's deal with that. So if I set this all equal to 0, I start with the GCF of x to the 4th power. That's going to leave x squared minus 8x plus 12. All right, so I bring down my x to the 4th power. Now I'm going to go binomial times a binomial. Now I'm looking at that 12, and I'm thinking this is either going to be 4 times 3 or 2 times 6, or 1 times 12. Okay, now considering I'm trying to get 8x, well, negative 8x, the 2 times 6 is going to be the one I'm going to choose. X squared has to be x times x. Okay, so let's go ahead with 2 times 6. All right, inner plus outer must equal the middle. So inner, I have 2x. Outer, I have 6x. To get negative 8, both of these have to be negative. So negative 2 and negative 6. Negative 2 times negative 6 is positive 12. So that means this is the correct factorization. Setting each of these equal to 0 is how you get the zeros. So that's going to give me x equals 0. Notice this was multiplicity 4 because it comes from x to the 4th power. But anyway, this is going to give me x equals 2 and x equals 6. So 0, 2, and 6 are my only 3 actual zeros. Okay, let's move on to number 9. If I set this equal to 0, the greatest common factor is 9x to the 4th power. So that's going to leave me with x squared minus 4. Okay, so now I need to set each of these equal to 0. So 9x to the 4th power equals 0. You know, I could just factor this more, actually. This is the difference of two squares, so I think most of you would probably notice that and just factor this down further as x plus 2, x minus 2. Now, x to the 4th power is equal to 0. X plus 2 is equal to 0. X minus 2 is equal to 0. This is going to give me x equals 0. That's multiplicity 4, by the way. X equals negative 2. X equals positive 2. So there's really 4 of these, and then 5, 6. So if you count this 4 times, because it's multiplicity 4, then that's your 6 zeros. Anyway, as far as unique zeros, it's just 0, negative 2, positive 2. Okay, last one. Okay, so finding the zeros means setting this equal to 0. The greatest common factor is simply 4, so I'm going to take that out. And that's going to leave x to the 8th power plus 4x to the 4th power plus 3 is equal to 0. Interesting. Okay, so now, even though this is x to the 8th power, I can still factor this the way I normally would. This is called quadratic form. When I have a trinomial and the first degree is double the second degree, like 8 and 4, or 6 and 3, or 4 and 2, okay? I can factor like I normally would. So x to the 8th power is going to be x to the 4th power times x to the 4th power. 3 can only factor as 3 times 1. Now, inner plus outer must equal middle. So inner, I have 3x to the 4th power. Outer, I have 1x to the 4th power. So if I just let them remain positive, that will give me 4x to the 4th power. So that's what I'll do. I'll let them remain positive. Positive 3 times positive 1 is positive 3. So that means this is the correct factorization. Notice that x to the 4th power plus 1 cannot be factored any further. This is not the difference of two squares. This is the sum of two squares. And that can't be factored anymore. What I can do is set each of these factors equal to 0. You can't set 4 equal to 0, right? Because 4 is a constant and it simply does not equal 0. But with the rest of them, I can set x to the 4th power plus 3 equal to 0 and x to the 4th power plus 1 equal to 0. Subtracting 3 from both sides gives me x to the 4th power equals negative 3. Subtracting 1 from both sides gives me x to the 4th power equals negative 1. In both cases, I have no solution. All right? An even power makes everything positive. There's no way you're going to take something, raise it to an even power, and then get a negative number. There's nothing to the 4th power that will give me negative 1. So, actual zeros, there are none. Alright guys, that's going to do it for this video. Go ahead and click here in the red apple to watch the next video. Click in the green apple to subscribe, or click the yellow apple for the full playlist.